Right, today we're going to cover the Physics Paper 6 Alternative to Practical, and this is for the Cambridge International Examinations IGCSE exam. There we go. And this is from May-June 2017. And this is variant 2. So the code is 0625/62. There we are. Let's begin.
Ready.
Question 1. The class is investigating the resistances of two resistance wires. The circuit used is shown in figure 1.1. A. A student places a sliding contact S on the resistance wire AB at a distance L equals 0.2 meters from point A. She measures the current I in the circuit and a potential difference V across the circuit, across the length L equals 0.2 meters of resistance wire. Figures 1.2 and 1.3 show the voltage and ammeter readings. 1. Write down readings shown on the meters in figures 1.2 and 1.3. There we go. So it's asking us to take the readings from the two images underneath, and that'd be the view that we would have if we were looking at the dials on the readouts on the voltmeter and the ammeter. So let's see if we can get the readings from that. Now, the voltmeter, it's got a scale which is broken down into every 5 little jumps gives us one large number. So that means each one here, if there's 5 jumps to get to 1, each one's got the value of 0.2. This is 4 in, so that's actually 0.8 volts. There we are, in there. Over on the ammeter, I've got 0.6 here, 0.8 here. This other large number there is actually 0.7. Now, looking at that image, the arrow is 2.5 points in. So it's exactly in the middle between 0.6 and 0.7. The reading here is 0.65 amps. There we go. So the voltmeter, 0.8 volts, and the ammeter, 0.65 amps. Now, part 2. Calculate the resistance R of the length L equals 0.2 meters of resistance wire using the equation R equals V over I. Well, let's look at that. R equals V over I. R equals 0.8 volts divided by 0.65 amps. Well, that gives me 1.23 ohms, but let's look at this. This is one significant figure. This is two significant figures. So the best I can hope for here is to write down to two significant figures. So I should write at this point 1.2 ohms. There we go, 1.2 ohms to communicate my confidence in that value there. So that should be to two significant figures. Excellent. Let's move on to the next bit. B. The student repeats the procedure using the distance L equals 0.4 meters. Her results shown is R equals 2.54 ohms. Calculate the difference between the two values for the resistance R. In the previous question, we calculated the value of R, and it was R equaled 1.2 ohms. Now this is a problem because I can't really do the equation 2.54 minus 1.2 to get the answer, because a calculator will interpret that as 1.20. So really what I need to do is add on the extra significant figure for this calculation, and then that becomes 2.54 minus 1.23. So here I have to use 3 significant figures for that second part for this calculation. A little bit of an unusual situation there. So that gives me an answer for the difference of 1.31. Key point, units. There are no units down there. So ohms. Let's write it in. Now, suggest a relationship between the length L and the resistance R of the wire that matches the results within the limits of experimental accuracy. Okay, well, here the length 0.4 meters is twice the original length, which was 0.2 meters. And the original value that we had was 1.23 ohms. If we take 1.23 and we multiply it by 2, that gives us 2.46 ohms, which within the limit of experimental accuracy is really similar to that value, isn't it? We'd pretty much say it's the same. So what does that mean? Well, that means within the limits of experimental accuracy, for this part 2 of this question, we would say that the length is directly proportional to the resistance. As the resistance doubles, as the length doubles, the value of the resistance doubles. So let's write that in. So there we go. The length is directly proportional to the resistance. Part C. Using the same method as in A, the student determines the resistance R1 of the resistance wire AB of total length L equals 0.5 meters. She then uses a short lead to connect points B and D. She uses the same method again to determine the combined resistance R2 of the resistance wires AB and CD connected together. Use the student's results to compare the resistance R1 of wire AB with the resistance R2 of wires AB and CD connected together. Okay, so let's just look at this. There's a couple of things. One, what's happening? Our student is jumping these two parts down here together. She's attaching them together and taking the readings there. All right. Now, are we expected to do anything with this? Are we expected to work backwards and create some awesome relationship between the two? No. What we're being asked to do is compare this number and this number. And what we can see is that, looking at that, R1 is about equal to 2 times R2. There we are. That's literally it. So they're explaining what's happening, but that's not what they want you to look at. They want you to look at the two values, value for R1 and the value for R2, and compare them. And if we look at that, R1 is about twice the value of R2. So tick the box next to the description that closely matches the results. There we are. R1 equals 2R2. Excellent. D. Suggest 2 reasons why different students all carrying out the experiment carefully with the same apparatus may not obtain identical results. Well, I'll tell you one thing that will affect it. If the wires are different temperatures, that will affect the value for the resistance. So the wires may be at different temperatures. There's one. Well, what's another problem we could have? Trying to measure these wires to the nearest millimetre is very challenging. It's very frustrating and it can be quite annoying. But it's tricky. It's tricky to do and it's tricky to get to the nearest millimetre, so that can present a problem as well. Let's put that down. There we are. There's 2 reasons, so it's difficult to measure the wires to the nearest millimetre. Now, anything else? Well, maybe the cell, the battery that the students are using, they'll have different levels of power left in them, so the cell itself may be running out of power. There's another one. All right, let's move on to the next question. Question 2. The class is investigating the refraction of light passing through a transparent block. A student is using optic spins to trace the paths of rays of light. Figure 2.1 shows the student's ray trace sheet. There we are. Sheet of paper with a block on it. A. On figure 2.1, draw and label a normal NL at the centre of side AB. Label the point E where the normal crosses AB. Label the point M where the normal crosses CD. Okay, let's run through this and start. So the first thing it wants it to do is draw a normal line at the centre of side AB. If you find these instructions a bit tricky, don't worry, it's the way they're written. Not intentionally to be tricky, they're just a little bit obscure. Once you've had a look at running through it once, it'll all make sense. At the moment, it's almost a mess of words, so don't worry, we'll run through that now, and that should make you a bit more confident. Now, if you want a bit of fun, I did actually run through this at one point, and if you do a search for Morpheus versus IGCSE Physics, I think sometimes that's how it can make you feel. Have a watch of that, see if you like it, I guess. A little bit of fun to help you with your revision. Now, let's do our normal line, which is halfway across side AB. There we are, so I've drawn that normal line in now. What I'll do, I'll put a link to that other video in the description below. So then, if you fancy a break, a little bit chance to recharge the battery so you can have a look at it. Now, we've drawn a normal line. It says draw and label a normal NL. Okay, so we have to label it still. Let's do that now. There we go, it wants us to label it NL, so N, and then we'll come down slightly and label the other side L. There we go. Alright, so we've done that first bit, draw and label the normal NL at the centre of side AB. Done. Label the point E where the normal crosses AB. Label the point M where it crosses CD. Okay, so E and M. There we are. So those points have been labelled now. What we've done all the things being asked for in that section, so we tick that off. The next part, draw a line FE to the left of the normal and at an angle of incidence I equals 40 degrees to the normal. Alright, so let's do that. There we are, that line has been drawn, the angle here is 40 degrees and it wants us to label it FE. So there we are, that's now done and labelled. So what I'm going to do, of course, is tick that to say it's done. So I now know it's done and I can move on. Label the positions of two pins P1 and P2 on FE on the line that we've just drawn, placed a suitable distance apart for accurate ray tracing. Okay, so if you ever do these questions and you wonder, well, how far is a suitable distance? They've already shown you because they've got two pins, P4 and P3, so about that far is pretty suitable. And in general, about as big as you can make it on the line without it being a problem. So there we go, one there, and one further down much closer to the edge, that's it. And we have to label those P1 and P2. Alright, let's move on to the next part. First we'll come down here and just put a little tick there so we know that that's done as well. B. The student observes the images of P1 and P2 through side CD of the block, so that the images appear one behind the other. He places two pins, P3 and P4, we've already seen them, between his eye and the block, so P3 and P4 and the images of P1 and P2 are seen through the block and they appear one behind the other. So the positions P3 and P4 are marked on figure 2.1, we've seen them. Draw a line joining the positions of P3 and P4 and continue the line until it meets the normal line NL. Label the point K where it crosses CD, so let's do that. There we are, so we've drawn the line that goes all the way up till it meets the normal, and now we have to label the point K where it crosses the line CD. There we go. So if we look down here we can see that that is everything we had to do there. Draw a line joining positions P3 and P4, done. Continue the line till it meets the normal line, done. So that's done, that's done. Label the point K where the line crosses CD, done. Okay, so that's now done. Everything else is a description. Okay, C. Measure and record the angle alpha between the line joining the positions P3 and P4 and the normal line. So let's do that. So for this, of course, we take out a protractor, measure this angle here. There we are. What we find is that gives us a nice 40 degrees. So let's just write that in. Remember, of course, the units, because there are no units down there. Next part, measure and record the length x between the points M and K. Right, so we're being asked to measure this length here, between there and there. Now, when I did that, I get the value of 15 millimeters. Don't worry if your value's out slightly there, because you're probably going to be doing this on a piece of paper you've printed out. So the mark scheme in the back says 17 millimeters plus or minus 2 millimeters. So I would get a mark there. Don't worry if yours says 15 or 16 or 17. That's okay. It can even go as high as 19. It shouldn't, but it could. So why is my answer different to the answer in the back of the book? Because the picture itself has been rescaled when it's been printed onto this paper. This is not an exact copy of the exam that someone took a couple of years ago. This is a printed PDF copy going onto letter size paper, so it's rescaled it. So I'm not too worried about that, and you shouldn't be either. D. The student repeats the procedure but with the line FE to the right of the normal. He measures the angle beta between the line joining the new positions of P3 and P4 and the normal line. He gets 41 degrees. He measures the length Y between M and a new position of K and gets 21 millimeters. A student, so let's just very quickly write down what we got earlier on so that you can see a direct comparison when they're next to each other. I get 15 millimeters here and 40 degrees here. So these are pretty close. These are pretty far apart though. A student suggests the results for alpha and x should be the same as the results for beta and y. State whether the results support this suggestion. Justify your answer by reference to the results. Okay, well, you know what? I'm going to go ahead and say no. The angles are similar, but look at the difference between the value of y and the value of x. That's quite a sizable difference. So I'm going to say no, these results do not support this suggestion. And why not? Well, I'm going to say that the results are outside of the experimental error. There's a 6 millimeter difference between x and y. X is 15 millimeters and y is 21 millimeters. This is too big for experimental error. So there we go. There's my answer. No, the results do not support the suggestion. The results are outside of the limit of experimental error. There's a 6 millimeter difference between x equals 15 millimeters and y equals 21 millimeters. This is too big for experimental error. Now, just to be clear, if you think that they could be the same, that's okay. You would just say, yes, the results support this suggestion. The results are inside the limits of experimental error, and then you'd quote the values as well. You would still get the marks. All right, let's move on to E. Suggest one precaution that you would take with this experiment to obtain reliable results. Well, number one, always a one that comes up, use the base of the pin. Yeah, so use the base of the pins. Other ones that would get your mark, use a large pin separation. Or ensure the pins are vertical. They would all get your marks. We only need to write one down, so I've only written one down. There we go. Let's move on to the next question. Question 3. The class is investigating images formed on a screen using a lens. Figure 3.1 shows the apparatus. There we go. We've got a little lens, illuminated object, and a screen at the other side. The lens has a focal length of 15 centimeters. Suggest a suitable distance d between the illuminated object and the screen in order to form a clearly focused image on the screen. Okay, so let's just have a look at that. So we're being asked to suggest a distance, here we go, between here and here. So we're being asked to suggest a value for that distance here. Alright, so what we need to do maybe is have a little bit of a look at how lenses work and how we get little images from them. So here we go. Got a little lens there, thin lens, and got a focal point here, and a focal point about the same distance over the other side, and then I've got a distance of about 2 focal lengths away. So 2 focal lengths in either direction. Now if I put an object here, what I would expect to happen is it will create an image of the object. Over here it will be inverted, it will be the same size, it's 2 times the focal distance away, the focal length away. So it's 2 focal lengths. And this is our focal point F and our other focal point F there. Now, as an object moves closer, what happens is it's not the case that the image moves closer, the image actually moves further away. There we are, we'll probably get an image around about here. And the way that works is we have, of course, our 3 construction lines coming along here. This one coming down there. We've got one going through the centre of the lines at that point, and then down through the focal point the other side, and one coming through the focal point here, I'm going, oops, it's not quite a straight line, there we are, going along there, and they all come together roughly the same spot, and that's where the image will be. Well, they should all come together at the same spot, but this is a drawing on a tablet on a computer, so it's lucky they come together on the same screen. But nonetheless, if they do, they come together on the same spot, and that's where the image is formed. So what does that mean? Well, as I get closer to that second focal point, or the focal point on the left-hand side, what actually happens is the image gets bigger and further away. When I reach that focal point here, when I reach there, what happens is no image is formed, and as I go inside this area, we get a virtual image formed. So a good number, it looks like to me, would be 2 times the focal length on one side, so 2f here, and on the other side, say up to there, 2 times the focal length there will do the job, which would mean I'm really looking at an ideal situation. It would be about 4 times the focal length, which is just 4 times 15 centimeters, which is 60 centimeters. There we go. So that seems to me like that would be a good number to put down for the distance d. Alright, let's do that. There we are. Okay, so I've gone for 60 centimeters. I've picked 60 centimeters, and you can see why I've chosen 60 centimeters because of the little drawing I've done in the top right hand side. Now, the mark scheme says anything between 50 centimeters and 2 meters will get you the marks. That's absolutely fine. So you can see where the 60 centimeters come from. Why would you not go less than 50 centimeters? Because you get closer and closer. As you get closer to the focal point on that left hand side, the image gets bigger and you have to be further away anyway. A good number is those 4 focal lengths away. That's really ideal. Okay, let's move on to the next question. B. The student places the lens, as shown in the diagram, a distance u from the object. She then moves the screen until she obtains a clearly focused image on the screen. It is difficult to decide on the exact position of the screen that gives the best image. Explain how you would find the best position for the screen as reliably as possible. Alright, well, let's look at that. Here we are, so a little 1 mark question. And that's actually key here, because it's asking us how we would find the best image on the screen. The only thing you can be doing is move the screen forwards and backwards until you get the best image. That's literally it. That's the answer. And there we go. Slowly move the screen back and forth to find the best position. Excellent. C. Another student uses a different lens and obtains these readings. U is 15 centimeters, V is 29.7. Calculate the focal length f of the lens using that equation there. F equals uv over u plus v. Include the unit and give your answer to a suitable number of significant figures. Ooh, significant figures, we do like them. Let's give this a go. So let's substitute in the values for u and v that we have and see what answer we get. There we go, so we get 15 multiplied by 29.7 divided by 44.7. Now, key point. At the top, we have centimetres, 15 centimetres multiplied by 29.7 centimetres. That gives us centimetres squared. And on the bottom, we have 44.7 centimetres. So, the unit of our final result will be centimetres. And of course, we have to write the units in because there's nothing there. And our final answer will be 9.97 centimetres. And I'm going for 3 significant figures. Why 3? Well, because that's got 3 significant figures, that's got 3 significant figures, and that's got 3 significant figures. There we are. 9.97 centimetres. 3 significant figures. Excellent. D. Suggest one difference that you would expect to see in this experiment between the appearance of the object and the image. Well, it's a projected image. Through a single lens, it's upside down. So the image will be inverted. You could also say it's been magnified, or it's fainter, or something along those lines. They're all correct. It's just asking for one difference that you might see in this situation. E. Which of the following procedures A to F are sensible for this experiment? Oh, let's look at that then. A, carry it out in a darkened room. Yes. Always darkened rooms whenever we're doing these light experiments. B, close one eye when taking readings. No, everyone knows you have to close one eye and stand on your head whilst looking backwards through a mirror. Okay. C, draw thin lines. That's not a bad thing, except there are no lines being drawn for this experiment. That would be the previous question. Ooh, see that? Almost fell for that. No. D, fix the rule in position on the bench. That's actually a good idea, because otherwise it moves all the time. It's really annoying, especially if you're in a dark room. How are you going to fix that? E, make sure the pins are at least 5 centimetres apart. We don't have any pins. Stop trying to trick me. Now I know you're doing it. F, repeat the experiment using different values of U and determine an average value for F. You know what? That's actually a pretty good idea. Repeat the experiment, take lots of readings, and average. Excellent. Let's move on to the next question. Question 4. The class is investigating the principle of moments. Figure 4.1 shows the apparatus used. So we can see there's a big meter rule balancing two weights at either side and a pivot just off centre at the 45 centimetre mark. A. A student places a load P on the meter rule at the 5 centimetre mark. He then places a meter rule on the pivot at the 45 centimetre mark. He places a load Q on the rule and adjusts it so the meter rule is as near as possible to being balanced. Okay, so he measures the distance A between the centre of load P and the pivot and the distance B from the centre of load Q in the pivot. He repeats the procedure, placing the load P at the 10 centimetre mark, 15, 20 and 25 centimetre mark. He keeps the pivot at the 45 centimetre mark each time. And we've got a bunch of readings here. So the readings are recorded in table 4.1. So there we go. There's all the readings that have been recorded. Part 1. Plot a graph of B in centimetres on the y-axis against A in centimetres on the x-axis. Ooh, start both axes at the origin 0, 0. So start both axes at the origin 0, 0. There we go. Alright, so let's give that a go and we'll put the pointers down. Right, there we go. That's all the points down. We've got our axes either side. We're starting it from 0, 0, which is a key point. And that actually makes our lives a little bit easier. The fact we've been forced into that. We just chose a nice little scale, which is every 10 small squares, every big square, is a value of 10 centimetres. And that happens to work the same in both directions, both axes. Okay, let's see the next question. Next part of this question. Right, 2. Draw the line of best fit. Alright, let's do that now. There we are, there's a line of best fit. B. A student suggests that A is directly proportional to B. Now that's an interesting statement. State whether the readings support this suggestion. Justify your answer by reference to the graph line. Okay, so why is that an interesting statement, that A is directly proportional to B? Because A being proportional to B is just a straight line. But if A is directly proportional to B, that means it goes through the origin. 0, 0. That's what we would expect to see. It would travel through the origin 0, 0. So let's have a little bit of a look at our graph again. There we are. We can see, looking at that, it doesn't go through the origin. It goes through 5 centimetres. That is definitely not the origin. And it's not out by a small amount. The line, the straight line, does not travel through the origin at all. So let's complete that answer. There we are. So no, the best line fit does not travel through 0, 0. So the readings do not justify the suggestion. C. The student uses a balance to measure the mass m of the meter rule, and it's 120 grams. Calculate the value of m times x, where x is 0.05 Newton centimetres per gram. Alright, so what it's asking us to do is multiply those two out. So we're finding the value of mx, which is just 120 grams multiplied by 0.05 Newton centimetres per gram. And that actually gives the answer of 6.0 Newton centimetres. Use the value of A in the first row of table 4.1 to calculate P times A, and it's given us a value for P here. P is the weight of load P. Calculate the answer and include the unit. Alright, let's do that then. So what we've got is we have a value for P which is given of 1.00 newtons multiplied by A, which is the first row in table 4.1, and that actually gives us a value of 40.0 centimeters, which gives me a value of 40 Newton centimeters, because we're just multiplying these two units together in cm. Use the value of B in the first row of table 4.1 to calculate Q times B, where Q is 0.8 newtons. Q is the weight of load Q. Alright, so let's do that. That's 0.80 newtons multiplied by 42.5 centimeters. And that gives us a value of 34 Newton centimeters. There we are. That's it. There's my answers. D. A student states that PA should equal QB. So they are the two values that we just calculated out. Look carefully at figure 4.1 and the information in C and suggest what the student has not realised. There we are. So the student's taken some measurements, they've moved the weights around and back again and made sure everything balances. But if you look closely at this metre rule, what you will see is it's not at the 50 centimetre mark. It's at the 45 centimetre mark, which means that the weight of the ruler itself is producing a moment. So the weight of the ruler. And that's not being taken into account. So the mass of the ruler has not been taken into account. That's what's going to create the problems with their answer. Because it's clear, if we come back down, that these two values here are not equal to each other. 34 and 40 are not equal to each other. Why not? Because the student didn't take into account the mass of the ruler in his calculations. There we are. Let's move on to the next question. Question 5. A student is investigating the effects of drafts of moving air on the rate of cooling of hot water. The following apparatus is available to students. An electric fan with 4 speed settings. That's good. 4 speed settings. That's going to be quite handy because we're going to want to change the amount of draft that there is, the amount of moving air. So those two are going to directly connect. 4 different settings means 4 different types of draft, so 4 different strengths of draft we can have. And we'll probably do a control one as well. Supply of hot water, good. Thermometer, always very important. Beaker, measuring cylinder, stopwatch, again very important. So what I'll do is I'll do this for a fixed period of time. Clamp, boss and stand. Not sure if they're necessary for that one. What I'm thinking at the moment, because I have to investigate the effect of drafts on the rate of cooling of hot water. So that means we're going to have some hot water, if you like. There we go. In a beaker. Of course that's going to be hot. And what we're going to do then is put a fan. There we go. Say a fixed distance from the beaker. Let's make that 20 centimeters. And then we're going to turn the fan on so it's revolving, it's blowing air across the beaker. Now, top of that I'm going to have my stopwatch. I'm going to measure 5 minutes. 5 minutes is a pretty nice number. And on top of that, I will need a clamp, boss and stand, and I'll tell you why. What I'll do is I'll put a clamp stand here, and I will hold a thermometer in the middle of the water so it's not touching the sides or it's not too high up. There we are. Okay, so that ought to work. And I'll probably just have it set up so maybe I've got the steam start temperature, time for 5 minutes, and we'll see how long it takes to, well, so I'll probably set it up so I've got the same start temperature, then I start it off time for 5 minutes, the end of 5 minutes, I'll measure how cold the water is, how much it's cooled by, so the new temperature of the water. Alright, that's pretty doable, and then I'll change the fan speed setting, and we'll repeat that, and then afterwards we'll look at the table, see which one has the greatest temperature drop for that 5 minute time period. Alright, so let's look at that. That seems like a good idea, good way to do the experiment. So we'll describe briefly how to carry out the investigation. That's fine. We'll redraw this picture a bit further down. State the key variables I'd like to control. Okay. Well, one, I think start temperature, amount of water, and cooling time. Let's set that up to be 5 minutes. Let's put the start temperature at 70 degrees Celsius. That's a good number to have. Draw a table, tables with column headings. Okay, that's good. What information we're going to want to record? Well, start temperature will all be the same. Time to cool down is going to be 5 minutes. So, what's going to be the key points? Well, one is going to be the fan speed. It's cooling for 5 minutes, so that's all fixed. The start temperature is fixed as well. I think the final thing we're going to want is the temperature, I think. The final temperature, because the 5 minute is encoded into the plan. Now state how you would use your readings to reach a conclusion. Find largest temperature difference, I guess. See what's actually identifying here. Looking at the cooling of water. So find the largest temperature difference. This is the most effective form of cooling. Alright, so now I've written all that down, done a little sketch at the side. I'm now ready to develop my method properly. First things first, let's draw it all out. Same as we did above, but this time we'll make it a little bit better. So there we go, there's the diagram. We've got a clamp stand and boss on the left hand side. That's holding a thermometer which is suspended above the base of the beaker. So that's in the middle of 250 millilitres of water. There is a fan on the right hand side, and that's separated from the edge of the beaker by a distance of 20 centimetres. Okay, now first things first then, of course, what we want to do is set up the equipment as in the diagram above. So there we go, there's my first step, set up the equipment as above. Now I'm going to start labelling steps because I'm going to want to reuse them. There we go, so step 1, empty any water from the beaker, of course, because we're going to repeat all these steps. Step 2, measure 250 millilitres of hot water into the beaker. And step 3, this is where it starts becoming more specific. Once the temperature of the hot water reaches 75 degrees Celsius, start the stopwatch and start the fan. There's a bit missing in part 2 there. What I'm going to want to do in part 2 is ensure that the fan is 20 centimetres away from the beaker. Right, so there we go. We ensure the fan is 20 centimetres from the beaker. Once the temperature of the hot water reaches 75 degrees Celsius, start the stopwatch and start the fan. Now, what I'm going to want to do then is measure a time period of 5 minutes, and at that point measure the temperature and record all the information in the table underneath. There we are, so once 5 minutes has passed, record the final temperature in the table below. The other thing that we're going to want to do at that point, we'll call it step 5, change the setting on the fan and repeat all the steps until all the settings have been tested. So there we go, change the settings on the fan and repeat the steps until all of the fan settings have been tested. Okay, now we're ready to construct a table. On we go. So I'm just going to design a table in the space at the very bottom so that then there's no conflicts or lack of space for me to write. Now I'm going to need to record the final temperature of the water, and I'm going to need to record the fan speed that the setting that's on. So that's two very important things. The time for 5 minutes is set as a part of the method, so I could, if I wanted, write in time 5 minutes for each of them. You don't really have to. If you want to, sure, go for it. And there we go. What I've done, rather than write down a whole section, I've put fixed time of 5 minutes, fan setting 0 to 4, final temperature of water in degrees Celsius. Okay, so now the fan setting and the final temperature of water should give me all the information I need. So what I want to do in my final bit of the method is write down how I'm going to compare the information. And there we go. Compare the final temperature of the water for each of the trials. The smallest value here will identify the most effective fan setting to cool the water. That's it. I think that rounds off that experiment quite nicely. Alright, hopefully you liked that. Hopefully you found that useful. If you did, please feel free to like and subscribe. And if you've got any questions or anything you'd like us to cover, please stick a note in the comment section underneath. And you know what? Have a great day.